So we're going to start off. What we're doing right now is we're going to think about a new way of thinking about mathematics. And so when you all started learning about mathematics, the first thing you did was you learned how to count, right? So how do we do that? Excellent. Oh, you're already ready. So 1, 2, 3, 4, 5, and so forth. I like this red one. Try this in black. 1, 2, 3, 4, 5, 6, so on, 9, 12, and so forth. You just keep counting, and sort of surprisingly, you found out at one point that you could go all the way up to this as long as you want. You can go up to infinity. And then at some point, you learned that there was another number that no one had told you of. What was that number?
Infinity?
Infinity is not technically a number.
0.
0. Remember when you learned about 0? Humanity learned about 0 about 6,000 years ago. It was invented in India, 0. It's an extremely important concept. For then, as far as we know, people didn't really understand it as a number in the same way the other ones were numbered. But we understand it as a number. Once you have this idea, then you can imagine doing the exact opposite in the other direction. And someone told you that there are these things called negative numbers, right? Which work exactly the same way. -1, -2, -3, 4, 5, 6. We'll just keep going to 9 and 12. Right? You could fill in the rest, right? And at some point, someone sort of showed you all this, and it was amazing. You had this idea of this number line, and then each of these numbers were there, right? These numbers are the B in scientific notation. Those are the only numbers you're allowed to have when you write scientific notation. Remember I said scientific notation is A times 10 to the B? B is only allowed to be these numbers when we write things down. And that's a useful thing to keep in mind. So we're counting like this, but there's another way to count. And that other way to count is called logarithmic counting. Let's write it up here. Logarithmic. So you've all taken mathematics and know what a logarithm is. You've heard about it at least, perhaps remember. It's shown up at some point in your studies, logarithm. We don't actually have to know what a logarithm is. We're not going to use them. But we do need to understand something about the concept of it. So that's what we're going to do. Logarithmic is a different way of counting or measuring than what you're used to. This is the standard, we can call it arithmetic way of counting. Now we want to count logarithmically. And when we count logarithmically, it's sometimes best to think about sort of the scenarios where it would happen. And one of the best scenarios I've thought of to start us off is we start off with rabbits. Imagine that one rabbit can have 10 offspring. We won't worry about how it happens. That's just the case. If you have one rabbit, you wait a little bit, soon you'll have 10 offspring. Right? And assuming that there's enough food and you don't have to worry about death so much, you could imagine counting generations of rabbits. Right? Instead of counting the actual number of rabbits, we might want to count the generations. Why? Because the actual number of them gets to be enormous too quickly. So let's try that. Let's imagine this scenario where we start off with one rabbit, and then each rabbit has 10 offspring, and see where that takes us. So to say that we're starting off with one rabbit, we're going to start at 0. And 0 with 1, the relationship between 0 and 1 is done by this. We'll say 10 to the 0. Right? Which is the same thing as 1, which is the same thing as O-N-E in English. Right? This is all synonymous. Right? This is the arithmetic one, but 10 to the 0, 1, and 1 are all the same thing. You've all learned that before, right? That's something you've seen. That's the first generation. Well, really, we call it the 0th generation. That's an awkward word. But in any case, it's the thing that we're starting with. We're starting with 1. The next generation, first generation. How many rabbits are there? 10. That's 10 to the 1. So that 1 means first generation. That's the same thing as 10. or we call that 10. Second generation, how many rabbits are there?
100.
100. Why?
10.
Because each rabbit has 10 offspring, and there are 10 rabbits. So there's 100 now. 10 to the 2. 100, also known as 100 in English. Third generation, 1,000. 10 to the 3, 1,000. Fourth generation. Now see, we've only counted to 4 and we're already at 10,000. This is why logarithmic counting is helpful. Because if you imagine trying to count to 10,000, that's going to take you a while. But it only had to count to 4 to get there already. 10,000, right here, 10,000. 10 to the 5?
100,000.
100,000. That's the pattern, right? This is a pattern that holds whether you understood this thing about exponents or not. You can also think of this as 0 tens, 1 10, 2 tens, 3 tens, 4 tens, 5 tens, as long as you're doing what to the tens? Not adding. This is multiplying. So logarithmic counting is the counting of multiplication. It's a multiplicative counting. And because it does that, there's a lot of tricks that will happen when we actually go to calculate things. So this is 100,000. I'm running out of space here. Fortunately, when I get to 6, what's that number? Million. Has anyone ever seen a million of anything?
Mm-hmm.
Example. What have you seen a million of?
I said $1 million.
You've seen $1 million? I've never seen $1 million. Wow. Impressive. It's possible. You could see $1 million. It's a lot. Yeah? Anything else? You've seen $1 million leaves? How did you know there were $1 million?
There was more than $1 million.
There was more than $1 million? How do you know?
Because you can count. Each tree has a lot and you multiply.
All right, so you did a calculation as to how many leaves were on one tree and then extrapolated from that there was $1 million. Sure, absolutely. Yeah, I'm certain that many people have seen more than, maybe you weren't aware that you saw more than $1 million leaves, but if you did. About 1 million seconds. How many people have experienced 1 million seconds? How long is 1 million seconds?
6 minutes.
1 million seconds is pretty long. It's about 11.5 days.
Really?
So you've all experienced 11.5 days, but you probably haven't been counting second by second for 11.5 days. But if you did that, if you sat there counting 1, 2, 3, 4, for 11.5 days without breaks, you would arrive at 1 million in 11.5 days. That's kind of useful. So you've all experienced 1 million seconds many times over. Let's skip 7, 8. They're not so important. Let's go to 9. What do we call 9? What do we call 9? Billion. That's a billion. It's so many zeros now, right? That's another people you may have recall learning about scientific notation. It's the number of zeros. Is that number? That's one way of knowing about it too. That's fine. There are people that prefer to write out long. This rapidly becomes annoying, right? Because writing 9 zeros is already enough. 12 becomes ridiculous. We're going to be using numbers that go up to maybe 100. Does anyone know what 10 to 100 is called? There's a famous company named after it.
First letter.
G.
Google?
Google. Don't try to write out a Google. It takes a long time to write 100 zeros. But 9, this is, I'm not going to write them out, but you get the idea. You know how to do that. This is called?
Billion.
This is called a billion, right? At least in the United States it is. In Europe they call it something else, but we won't get into that. And then we'll just, for completeness sake, keep 12 here, 10 to the 12. 12 zeros, anyone know what that's called? Trillion, yes. All right, so that's all well and good. You guys know how to do all of that already. But what about counting in the other direction, right? We've already had positive numbers, we had this experience. What is the concept behind a negative number? Well, you think about the question in reverse, right? Negative numbers are just moving in the opposite direction. So when I moved in this direction, I was going up by generations. When I move in the other direction, I'm going down in generations. But if I think, I can't move back in time, another way of thinking about it is that I would have a population of rabbits, and then something would happen, and I would have only 10% of the rabbits afterwards. Do anyone know what that's called? When you start off with a population and you end up with 10% of that population?
Extinction?
Eventually, but before that happens, it's called decimation, right? That's where the word actually means. And you say, I'm going to decimate you. That means you're going to cut off 90% of the other person. Right? It's a pretty dramatic event, decimation. And so that's what's happening in the other direction. This decimating is happening. So if you imagine you started off with 1 million rabbits, and some event happened that decimated the population, how many would you be left with? Started with 1 million, decimation happens, then what do you have?
100,000?
End up with 100,000, right? Then you have another decimation event. You end up with 10,000. Then another, you end up with 1,000. Decimation is the subtraction. But really it's not subtraction. If we were thinking in arithmetic land, it would be what?
Dividing?
Is division, right? We're dividing by 10 each time, moving in this direction. We can take that logic all the way the other direction. If I start with 1 and I decimate 1, what do I get? Well, -1 in logarithmic counting, but what is it in? This starts off with 10 to the -1. What is 10 to the -1? 0.1. That's one way of writing it. What's another way of writing it?
10th?
1/10. Right? Or we can write it in English. Right? There's a nice symmetry here. That's why I wrote down in English 10. This is 10. Right? Literally means put it underneath. Put it underneath a division. Those are all the same way of saying the same thing. Right? So you may recall that the negative numbers, division, that's true in exponentiation, that's true. But this is where the logic comes from. The logic comes from counting. If I count up, right, I'm multiplying by 10. If I count down, I'm dividing by 10. And that's what's happening. Divide by 10, divide by 10, divide by 10, divide by 10. And I can continue. I can do exactly the same argument this way as I did the other way. So if I have -2, what is that?
100th.
100th. 1 over 100, which is 100th DTH. How about 10 to the -3?
1,000th.
Yep. Very good pattern. 1 over 1,000, 1,000th DNTH.
So decimation can only be divided by 10.
Decimation is technically division by 10. That's really its definition. Divide by 10. Done. Right? And you can continue on, 10 to the -4, 10 to the -5. Let's do 10 to the -6 here. 10 to the -6 is what?
Millionth.
It's 1,000,000th. As I stop writing things in zeros, I'll stop writing the zeros on this side. But the same logic applies. We want you to start working in this zone rather than in these zones. This is for learning purposes, but when you actually do the calculations, you're going to sit up here with those b's. The b's are going to be important. The 6, the -6, is much more important than whether you can write 1 over 1, 0, 0, 0, 0, 0, 0, 0. Right? Or 0.0000001. Right? So this is 1,000,000th. And then what's 9?
A billion?
A billionth. And what's 12?
A trillion?
Trillionth. Very straightforward, right? Not well explained, I don't think. I don't think that this is as well explained as it should be. But this is where the symmetry is coming from. You count up to trillion, you count down to trillionth. Right? We don't often think of it that way, but that's the way logarithmic works. You never actually reach 0. 0 is as far away from 1 as infinity. Right? You can't get there because you just keep dividing by 10 and dividing by 10 and dividing, and you never get to 0. So this is the property of logarithmic counting. Why do we do these things? Because this is also the property of nature, if you think of it. If I'm looking at the size of various things, I can get to very, very small, but I never get to disappear. Or I can get to very, very big, but I never get to infinite. Right? There's always some limit. There's always some point where I can say this is where it is, or this is where it is. and I can make comparisons between those. When I make comparisons between those, I want to use this form. Right? I want to use the exponentiated form, because you'll see it makes the mathematics a lot simpler. Any questions about this counting first, before I do some of the tricks with mathematics? So why do we do this? Before I do this, I want to point out a few other things before I erase this. These also come with prefixes. If you have ever looked into the metric system, you'll know that the metric system comes with prefixes and that it's also based on factors of 10. And it so happens that each of these factors of 10 have its own prefix. You may not be aware of it, but does anyone know a metric prefix? Metric system? Tell me a measurement in the metric system. Centimeters. So there's two parts to that. Meter is the base unit. Centi is the prefix. Centi means what? Doesn't mean 100. Centi literally means this number.
100th.
If you ever see centi, you are well within your rights of erasing the centi and writing 10 to the minus 2. That's all it means. It doesn't mean anything else than that. It means hundredth. Hundredth of what? Well, in centimeter, it's hundredth of a meter. That's all it means. Right? There's nothing more complicated. When you learned that there was 100 centimeters in a meter, what you were actually doing was just switching that centi out for 10 to the minus 2. That's really all it does.
So deci is 10th.
Deci is 10th. That's why decimate is, right? And so decimeter is a tenth of a meter. There's also letters that are associated with this. We won't use deci that much, but we certainly will use centi, so that's a small letter C. So if you see in metric prefixes a small letter C, you are well within your rights of changing that to a 10 to the minus 2 and being done with it. Other metric measurements. Inch is not metric. Inch is imperial units.
Liters?
What's that?
Liters?
Liters, but there's no prefix for liters, but that's perfectly fine. What? Millimeter. Milli is the prefix. What does milli mean? Thousandth. You want it to be millionth because it sounds like it, but it's thousandth. This is milli. M-I-L-L-I, otherwise known as lowercase m. Okay. If you see a milli anywhere, millisecond, you are well within your rights of replacing that with 10 to the minus 3. Right? A millisecond is a thousandth of a second. That's what it is. Other ones. How about automobiles? Go or kilometers. Kilo is which of these?
3.
10 to the 3. It's 1,000. This is kilo. And that's a lowercase k. Same thing. If you see a kilo, you can replace it with 10 to the 3 or 1,000, and you're done. Any others that people know? So the ones that we want you to know are certainly milli, centi, deci is fine, but it's not important. Kilo is important. Yeah?
What about inches?
Inches are a different unit. To convert from them, you have to know how many of a meter is in an inch or how many inches are in a meter. There's no simple way. It's not based on the 10 system. That's the problem. But in metric system, we are always based on the 10 system, so we'll always have a prefix and a base unit. That's part of the reason it's a nice way of talking about things. Any other ones?
What about mile?
Mile is also imperial, not metric. Right? There's an odd number, I think it's about 1.6 kilometers in a mile. So you can use that to convert back and forth, but it's not this simple prefix base unit thing. Yeah?
LBs.
Also, those are pounds, another imperial unit. We're really good on those
Whatever
imperial
ends in
units.
meter, right?
What's that?
Only whatever ends in meter.
Meter, liter. What else? Yeah?
So there's milliliter, right? And
Milliliter, right. Milliliter would be a thousandth of a meter. A thousandth of a liter. Yeah.
Micrometer.
It's the same thing.
Micro, here we got one, micrometer. People heard of micrometer before? What is micro? Or sometimes they call it micron for short. Ever heard of micron? Micrometer? Micro. What size is that, do you guess? It's smaller than milli.
8, 10 to the power negative.
8 is a good guess, but it's not. It's this one. It's millionth. This is micro. Now, because it begins with an M, you'd guess that the letter we would use would be M, but since we've already used it, they use a Greek letter. This is the Greek letter they use. It looks kind of like an M, but it's not pronounced M. This is mu. Okay, cats say mu, so that's the letter mu. And you'll see that from time to time. Again, if you see micro, you replace it with 10 to the minus 6. A micrometer or a micron is a millionth meter in the range of human hair. How about
Nano. We have nano.
excellent? That's a billionth. Nano. A nanometer is a billionth of a meter. That's a lowercase n. That's a little bit easier than micro. We don't. There is a one for the trillionth, but we won't encounter it. These are all in the appendix C of your textbook too. Through that as well. Nano, micro, millicenti, kilo. We'll also do billion and million. Does anyone know what the metric prefixes for million and billion are? If you deal with computers a lot, you know.
Megabyte, gigabyte.
Exactly. A million, roughly, bytes is a megabyte. Mega. Capital M. And a billion, roughly, bytes is a gigabyte. Giga. Capital G. Those are the only metric prefixes I'm going to ask you to use. But the reason I ask you to use them is because if you know what their translation is, you can immediately do some interesting unit conversions. We already did one, right? I've said how many centimeters are in a meter. Well, if I just look at the word centimeter, I get the answer. Centimeter is the same thing as 10 to the minus 2 meters. Right? That's the same thing as a centimeter. If I want to know how many meters are in a centimeter, I do a little bit of algebra. The algebra I do is I say, well, I want to know for 1 meter how many centimeters there are. So I want to get 1 meter on this side. How do I get 1 on this side? 1 times m. What do I have to do to get rid of this 10 to the minus 2, algebraically?
So you flip it to the other side?
I flip it to the other side. That's divide by 10 to the minus 2. Divide this side by 10 to the minus 2. When I divide by a negative exponent, what does it do? It comes out. So this means that 1 meter is equal to 10 to the minus 2 becomes 10 to the positive 2, 100 centimeters. That's why 1 meter is 100 centimeters. This is something like that. That conversion just happened just by looking at the word. I didn't have to do anything but look at the word.